Good afternoon. We are the Roads on Icy Worlds team, and today we are discussing our research about our rover mission to Jupiter's moon, Europa. For decades, people both within and outside the science community have dreamed about humans discovering life beyond Earth. That dream may be accomplished by investigating Europa's cold and icy environment. NASA scientists theorize that the interior ocean of Europa could sustain life. Our research was divided into two main aspects. First, we completed the Roads on Icy Worlds Engineering Challenge, which simulated a rover mission that incorporated robotics, programming, and sample collection. Then, we expanded the scope of our project by conceptualizing a realistic Europa rover using 3D modeling. Now we will introduce ourselves.
Hi, I'm Dejman. I'm a rising senior from Miami, Florida, and aspire to become an electrical engineer in the near future.
Hi, my name is Michelle Feng. I'm a rising junior in Allen, Texas, and I have an interest in math.
Hi, I'm Tamara Kasikovic, and I'm a rising senior from Old Bridge, New Jersey. I aspire to become a software engineer in the future.
Hi, I'm a rising senior from the island of Kauai in Hawaii. I'm interested in pursuing mechanical engineering.
Hi, I'm Kayla Rigal, a rising junior from Greenbelt, Maryland, and I hope to become an experimental particle physicist.
Hi, I'm Ava Sadasivan. I am a rising junior from Austin, Texas, and I aspire to pursue computer science and electrical engineering.
My name is Liliana Sanchez, and I'm a rising senior from Far, Texas, and I hope to someday become a mechatronics engineer.
Hi, I'm Karamoko. I'm a rising senior from Philadelphia, Pennsylvania, and I would like to become an aerospace engineer.
This is the mission patch we designed to represent our project. The mission patch displays our rover on Europa wearing ice skates to indicate Europa's icy surface. In the background is spelled Roads as a constellation, which is the name of the robotics challenge we undertook. Then underneath that is our team name, Ice Vikings, which is illustrated by the Viking helmet on our rover. Lastly, we created the mission patch in the shape of an octagon because we have 8 team members.
Now we will move on to the background of our mission. Europa is a moon orbiting Jupiter, dubbed a Galilean moon due to it and 3 other moons being discovered by Galileo. Europa has a subsurface ocean hidden underneath a water ice crust and heated by the mantle underneath.
A few of the challenges of a rover exploring Europa include the unpredictable terrain, low temperatures, and distance away from the Earth. Europa's oceans are above a hot rock layer, causing the heating of the oceans and the shifting of the icy surface. Europa's chaos region is very rugged and has many cracks and obstacles that the rover will need to maneuver. Due to Europa's long distance from the sun, the temperatures there are very low and the communication with Earth's mission team would be very delayed. So the rover would need to protect itself from the cold using insulation and have autonomous features.
But why should we travel to Europa? Scientists believe there is a good possibility that some form of life lives on Europa. Some evidence for this is the ocean underneath, which has been detected through plumes of water rising from Europa. And due to tidal forces, the ocean is heated, keeping it liquid and allowing for proper conditions for life to form.
Another reason for Europa's possibility of life is the magnetosphere. Jupiter's magnetic field is being disrupted by Europa, and scientists infer that it is because of an electrically conductive fluid, specifically salt water, under Europa's ice layer. Also, Europa's extreme conditions are suitable for some microbes that live on Earth, so life on this moon is realistic. One of the future missions to Europa is NASA's Europa Clipper, which is set to launch in 2024 and will send an orbiter spacecraft to determine if Europa is suitable for life. Another future mission is ESA's Jupiter Icy Moons Explorer, which is set to launch in 2023 and will make detailed observations about Jupiter's system and its 3 largest moons.
Next is the engineering component of our project, the robotics challenge Roads on Icy Worlds. Our project objectives were to keep a mission development log that we updated every day with our progress, to design, build, and test the samples, rover, and drone, build the Europa map, and construct barriers, and program the rover to complete the challenges autonomously. The objectives of the map were to first choose a landing site that we would deliver the lander to with the drone. After the drone completes its part, the rover autonomously collects the samples from the sites and returns them to the starting point.
Our team members calculated the important points and links needed to map out features such as barriers, landing targets, the point of interest, and sample sites. Our work included math applications like law signs, slopes, and area formulas.
We made the field map by putting together white poster boards. The total area of the map is 8 feet by 5 feet, and we left some excess to label the measures. This would make it easier for us when plotting the points for our barriers and sample sites. We built actual physical barriers to simulate obstacles. We also have this blue spot on the map that the rover is supposed to detect with the color sensor. So now the drone and the lander. We've tried multiple designs for the lander. Our goal was to create a loop on the lander that the drone would be able to hook onto. And then upon release, the lander would hit the ground and the drone would detach. We tested different weights for the lander to see which would fit the best with the drone. We figured it couldn't carry more than 30 grams. So our final design only weighed 27 grams. We had 2 drones in our possession, and we found that the smallest one was the most accurate to fly with. And that's the picture on the right. To carry the lander, we used a string first and taped it to the drone, but then the string would swing too much. So we decided to use a copper wire instead for stability, and we taped it to the drone. After adding all those elements, we were able to fly the drone safely. The drone would take off separate from the lander, then it would pick it up, carry the lander to the landing spot on the map, and drop it right on the target. And this is the video of our drone carrying the lander to the map.
We built our rover using the Spike Lego kit. None of us had ever worked with Spike before, so it was a challenge to learn how to use it and its new technology. But we were able to overcome this by following online tutorials, researching errors as we went along, and continuing through the engineering process through the building stages of the rover.
Once we had a better understanding of how to work with our material, it was time to conceptualize what our working rover would look like. We had a group meeting and decided on the following. The rover uses a 2-pronged lifting mechanism to collect 2 samples at a time, 1 on each arm. It has large wheels with strong tread, best suited for traversing Europa's icy surface. Lastly, it has a color sensor for the rover to identify potentially interesting samples. Specifically, because Europa is an icy moon, anything on the surface that is not white may contain minerals and should be investigated.
Version 1 of the rover development process. On the left is the Spike rover design we used to help build our own. However, we made some slight modifications in order to adapt it to our map project. Our biggest challenge with this was understanding completely how our model rover worked before moving on to make the modifications. We ended up flipping a few pieces and adding others for stability in order to get a 2-pronged lifting mechanism shown in the right.
Once we finished designing our rover, we started programming it. And just like any mission, we faced challenges, and we quickly realized that some changes needed to be done. The first challenge was the wheels. We used the wheels with no tread found in the Spike kit, but the movement with those wheels were not predictable enough. So we decided to use some other wheels found on an EV3 kit used in previous years that had the treads on it, and that fixed the first problem. Then the second problem was that even after we got the coding done, we were not able to be very precise with the alignment each time we tested it, and this messed up our measurements, so the rover's path would change slightly every time. We fixed this by marking some points and lines on the map to make sure that the samples and the rover were always aligned the same. Also, slowing down the rover speed and adding lots of pauses helped with precision. The last challenge was that the rover was unbalanced due to the weight on the front. To fix that, we replaced the ball at the front of the rover with a heavier one, and then the robot was balanced. We were then able to run our code fully, and after multiple tries, it finally worked.
Here's what the changes to the wheels, the ball look like, as well as the color sensor that we added.
And here is our final rover design.
Along with 2 planned orbiter missions, a Europa lander concept has been proposed, but it's not currently set to be built. Rather than a lander, we propose a rover that would have optimal mobility for ascertaining a diverse set of samples for analysis, rather than a lander being limited to one spot. A rover would also be best for mapping how terrain and meteorological conditions change across multiple areas of the icy moon. Therefore, our group decided to extend our project and conceptualize a future rover mission on Europa. Our mission has several objectives. First, we want to collect data on the surface of Europa to detect molecules and organic compounds, such as carbon or sulfur, that can indicate life. Our group is particularly interested in the plumes on Europa, since they eject water from beneath the subsurface oceans. Analyzing the areas around the plumes can provide insight into potential biosignatures in the icy water. The rover will collect data from a variety of sample sites to provide information about the various regions and geological properties of Europa.
Finding life on Europa is a possibility because it fills the requirements of water, essential elements, and energy, components that are crucial for life on Earth. Water dissolves nutrients and enables chemical reactions. For essential elements, life requires an array of biological elements to serve as the basic building blocks and material for growth and reproduction. These include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. A Galileo flyby detected most of these within Europa. It is also possible that asteroids and comets could have impacted the surface and deposited even more organic or carbon-containing materials. Lastly, energy is dispersed throughout Europa's surface since Jupiter projects radiation onto it.
We chose the Pool Crater as our rover landing site due to the evidence of water nearby from previous flybys. It's one of the youngest craters on Europa, so it hasn't been wiped away by geological activity, and it still retains bright white rays of freshwater ice. We selected a northern region of the crater for our area of interest because of the plumes of water observed there in 2014 and 2016.
Land at 271.4 degrees longitude and negative 22.3 degrees latitude. So be very close to an abnormally warm spot without landing on the rocky terrain of the crater. We had looked at multiple other sites with interesting areas, but due to a lack of information on the sites and the rough terrain, we had decided against them.
One of the biggest challenges with designing the rover was Europa's cold environment and icy terrain. While typical NASA rovers rely on a wheel mechanism called the rocker bogie, we opted for a new wheel design in which each wheel has independent mobility. This means it has a better range of motion to maneuver around obstacles in the terrain, which is particularly important because Europa's terrain is still not very well characterized. In addition, the wheels will have strong tread to prevent slipping on Europa's icy surface. As for the body of the rover, we chose a hexagonal shape so the rover would remain compact in order to keep the instrumentation insulated against the cold temperatures. To power the rover, we selected the battery used in the Dragonfly mission rover that will be launched to Titan in 2027. The battery is an RTG that will recharge a large lithium-ion battery and be held at the rear of the rover. Lastly, the rover has a drill to cut through the ice to collect samples and a robotic arm to aid in the analysis of said samples by the rover's instrumentation.
Rover instrumentation is often added in suites of 2 or 3 compatible instruments aimed towards one goal. The first 3 instruments we chose for our rover were for the detection of minerals and biosignatures. First, we have 2 different types of spectrometers. The mass spectrometer provides data such as molecular mass to interpret the elements and structures of the molecules making up the sample. The Raman spectrometer is a type of vibrational infrared spectrometer, meaning it studies the vibrations of molecules by recording what wavelengths of infrared radiation are absorbed, thus determining chemical composition of samples. Together, these 2 spectrometers should identify any signs of life at the molecular level in our samples. To provide visual context for the spectrometry data, the rover will have a microscopic imager to provide magnifying glass level detailed images of the samples. The next suite of instruments will provide data from the environment surrounding the rover in order to study the geophysical properties of Europa. This is important to understand not only as context for samples, but also for the growing fields of research in comparative oceanography and tectonics. The majority of environmental sensors on our rover are housed in one large instrument called the Environmental Monitoring System, similar to the one used previously on the Mars Curiosity rover. This provides a diverse array of meteorological data around the rover, including atmospheric pressure, temperature, humidity, winds, and ultraviolet radiation levels, as well as data on how environmental conditions vary across day, season, and location. The subsurface ice radar will use radar waves to probe under the ice surface and map the thickness of Europa's icy surface. This will give us a chance to study planetary geology and terrain across a range of meteorological conditions. The site imaging system will provide visual context for the variety of data being acquired. And lastly, the navigational camera will be housed in the same body as a site imaging camera, but use a different lens for a specific purpose, which is to give the rover the ability to drive itself autonomously.
Lastly, we have our conclusion, a wrap-up of our experiences.
One of the highlights of our SEAS journey was when the team was exposed to the real-life work of a NASA employee at the Johnson Space Center. Another highlight was when our team was excited to expand our project to encompass an additional research aspect, especially considering the future potential of this work.
How SEAS has inspired us. Before SEAS, I knew I loved programming. However, I didn't anticipate how fun it would be to combine programming with hands-on engineering to build our rover. Because of this, I've been inspired to pursue more hands-on engineering as a future career. I've also been empowered by the chance to participate in the full research process, work with incredible mentors, and get a sense of the exciting future work I could one day pursue at NASA.
As someone who comes from a community that does not have a lot of opportunities to pursue a career in the STEM field, I am extremely grateful for this opportunity to be a SEAS intern. This experience has not only opened my eyes to new possibilities, it has also secured my decision to continue to grow within the STEM field.
Being a SEAS intern was an incredible experience. Being here helped me secure my decision of wanting to be an electrical engineer. After being a part of this program, I grew to love all aspects of engineering more, both the hardware and the software. I was able to grow my ability to problem solve and to engage in projects that I'm a part of, to give it my all and be a valuable member of the team. I now have a better understanding of how a team works and how every member is important and needed for the project to work successfully.
SEAS has been for me a life-changing experience. It was a wonderful opportunity to get more exposure to the field of STEM. I got to meet with very talented people who had the same interests as me. I was able to learn from my teammates and mentors some very useful skills I would like to mention.
I'm extremely grateful to have had this experience as a SEAS intern. Coming from a place with not many STEM opportunities, the knowledge I have gained from this program is once in a lifetime. I will continue to apply what I have learned this coming career and on to the future.
Through attending the SEAS program, I've gotten the amazing opportunity to apply the everyday subjects and knowledge I learned at school to real-world problems, such as using math for mapping coordinates and locating landing sites of Europa. Collaborating with great mentors and STEM-passionate students has inspired me to think outside of the box, and this internship has given me exposure to how useful and rewarding STEM can be.
The SEAS program has given me an experience I have never had before. It has allowed me an opportunity to communicate and collaborate on projects with people envisioning similar career paths as I am. It has opened up a wide new door of possibilities in the STEM field and has given me the resources and skills to be successful as I pursue a career in physics.
SEAS has given me an amazing opportunity to connect with like-minded individuals and enrich myself in new STEM subjects. After speaking with a mission control specialist for the ISS at Johnson Space Center, my eyes were open to new career options at NASA. Being a part of this program also taught me how to conduct scientific research and problem solve, which will be incredibly useful for my future career as a software engineer. I could not be more grateful. These are the sources we use for our research. We would like to thank some of the important people and programs that made SEAS possible. We would like to give a special shout out to our mentor, Ms. Crenshaw, and the Mars rover mentor, Mr. Ralston, who helped us with our rover conceptualization. We would also like to thank Patrick Petty and Sherelle Webb for reviewing our research abstract. And lastly, but not least, we want to thank Margaret Baggio and Selena Miller for running SEAS and making all of this possible. We could not do it without you.